Hello and welcome back to QED and QCD. Today we'll be investigating photon scattering, or rather scattering processes involving photons. So scattering with photons. In particular, we'll look at E gamma goes to E gamma. Now, in order to do that, we'll have to first understand how to treat processes with an external photon, how to calculate amplitudes with external photons. So far, we have looked at how to do scatterings with an exchange of a photon. Now we have an external photon. So the first thing we look at is photon polarization. In particular, let's see what plane wave solutions we can find for the free photon. So we'll postulate, seek solutions of the form AFX is equal to a polarization vector e to the minus, and then e to the minus ikx. And then look, what solutions do we have to find for epsilon mu? We can even make a mu a solution or a function of k. Now, epsilon mu here we'll call the polarization vector. It is a vector in the sense that it has a mu index. Now, if we look in the Lorentz gauge, then the plane wave solution, we all remember what the Lorentz gauge is. But of course, it's not the Lorentz gauge, it's the Lorentz gauge. Says that d mu a mu is equal to 0. We have that the wave equation that a mu has to fulfill says that the D'Alembertian on a mu is 0. D'Alembertian is the d nu. Good. So this equation here imposes a constraint on k, because when we take the derivative with respect to d nu, we get a k nu down, minus I k nu, and then we take a derivative again, which gives us another minus I k nu. The two k nu's contract and give us a k squared. So this wave equation here imposes that k squared must be equal to 0. Now, the Lorentz gauge condition of d mu a mu gives another constraint that actually says that k mu on a mu must be 0. In particular, k mu on epsilon mu must be 0. Now, there's actually still some freedom left in choosing our polarization vector. This, of course, doesn't constrain the polarization vector completely. Because let's say that we had one solution for the equations here, k mu dot epsilon mu is equal to 0, then another epsilon that we could call epsilon prime, epsilon plus k, even with a scalar, would also solve this constraint. So if epsilon mu is a solution, then so is epsilon prime mu on this form for all values of lambda, because k squared is equal to 0. Now that therefore gives us the freedom to choose epsilon 0, the 0th component, is equal to 0. So this gives us freedom to require epsilon 0 is equal to 0, right? Because if it wasn't equal to 0, we would just set lambda such that k mu 0 times lambda was equal to minus epsilon 0, and therefore epsilon prime would have a 0th component. So then the requirement that k mu epsilon u is equal to 0 becomes a 3-dimensional requirement that k dot epsilon, just the x, y, z components, is equal to 0. So that means that the epsilon is perpendicular to k. So therefore that the polarization vectors are orthogonal to the direction of travel, and they're called transverse polarizations. So in order to span that space of solutions, we would have two polarizations. It's a 3-dimensional space, and we're looking for the one that is orthogonal to a vector, so that's 2 degrees of freedom. So we would have an epsilon alpha, alpha 1, 2. They are transverse to k, and they are chosen usually to be orthonormal, so orthogonal and normalized. With that condition, there's a useful relation saying that, for example, the sum over the two polarization vectors of epsilon alpha I and epsilon star, the same polarization, j, k, k, will be equal to delta ij only when they're the same xyz component minus k I k j. Normalized with a normalization here means it's a ki divided by the length of k, which is the ith component, and the length is of course equal to the energy. Now here the Feynman rule we had before, the Feynman rule for external fermions, the Feynman rule for an incoming photon. So if one has a Feynman diagram where there's an incoming photon connecting to a vertex, then the Feynman rule would be that you multiply by or contract with the polarization vector, and if you got a final state photon, outgoing photon, then the Feynman rule is epsilon star mu k. Good. When it comes to fermion spins, if you want to calculate the unpolarized process, then what one does is to calculate the total cross-section by averaging over the incoming polarization and summing over outgoing polarization. One can do the same thing for photons. So if we consider photons, then the scattering amplitude Im would have the form some amplitude, let's call it It's not the photon field, but just some amplitude. And because that let's say that there's an incoming photon k, then since that's a final rule for an incoming photon is an epsilon mu, then the rest of the amplitude, in order to give a scalar, must be another vector. And that vector will be just called a mu. That's the part of the amplitude that does not have the incoming photon polarization vector contracted. Now, this here is gauge invariant. And therefore, the right-hand side has to be gauge invariant. And what does it mean to be gauge invariant? That means that if we had replaced epsilon mu with epsilon prime mu equal epsilon plus k mu, even lambda k mu, then we will get the same result. We will get an invariant number. So if the left-hand side is invariant under the replacement or under a gauge transformation, then that means that on the right-hand side, so under a gauge transformation, Im goes into Im, but the gauge transformation here would leave the same a mu and then an epsilon mu plus lambda k mu. But this bit here we already know is m, so the contraction of a mu with k mu must be 0. When a mu is gauge invariant. So when we're calculating gauge invariant amplitudes, then the part of the amplitude that doesn't have the photon polarization vectors contracted, when dotted with the photon wave vector k mu, must be 0. And that's called a Ward identity. It's a result of the gauge invariant of QED that k mu, a mu must be equal to 0 when a mu is given by the amplitude. Like so. It's a useful test for the gauge invariance of the calculation. If you contract with the photon momentum and get something non-zero, then there's probably a mistake somewhere. Good. So we wanted to study now the process E gamma to E gamma. So, in order to calculate the scattering amplitude, we need to first draw all the diagrams. There are two. So what we have here is an electron line, then goes from initial to final state. So there's an E with momentum P, and here we say it has momentum P prime. And there are two places. Here there's a photon that comes with momentum K, and the final state photon has momentum K prime. So that's one diagram. The other diagram can be drawn, or all the diagrams can be drawn in many different ways. But one way of drawing the other diagram is to say we've got the incoming fermion, electron, the same way. I like drawing my diagrams such that the particles' positions on the piece of paper for final initial state is kept fixed. So of course then there's another way of connecting the two photons. You could say that the photon here connects to the vertex over here, and the final state photon connects to the vertex over here, like so. Now, we already know, we'll put this aside for a little bit, but because of this result here, we already know that if we square the amplitude, then the sum for alpha equals 1 to 2 of our matrix element squared, which is a mu epsilon mu squared, will be equal to sum alpha equals 1 to 2 a mu, and then the complex conjugate in nu, then we'll have the epsilon, the polarization vector for the mu, and the complex conjugated polarization vector with the nu. Using the conditions or the result of here, we can therefore write the result down here as every time we see mu is equal to 0, then we know that there will be no contribution because epsilon mu and epsilon nu are chosen such that the 0th component is 0. So that means that here we will get a AI I would say A star J, and then we're here we'll get a delta ij minus k hat I k hat j. Now the equation that a mu k mu is equal to 0 implies that AI contracted with ki here is equal to a0, right? Because the only way, or the only difference between a mu k mu and ai ki is the 0th component is included in a mu k mu, it's not included in ai ki. So the fact that this is equal to 0 means that ai k hat I is equal to 0 because that ai ki must be equal to a0 k0 from this equation here. And when we take this one downstairs and normalize it, we get exactly this one up here. Now therefore, the sum from alpha equals 1 to 2 of a mu epsilon mu alpha k squared will be equal to ai minus a0 which is equal to minus a mu a star mu g mu. Now, this could be done for each photon in turn if there were more in the process than just a single photon, and therefore one finds the general result that when calculating gauge invariant amplitudes, whenever one sees a sum over alpha 1 to 2, epsilon mu alpha, epsilon star nu alpha, then one can replace that by minus g mu nu. This is true only when the amplitude that one looks at is gauge invariant, so it doesn't hold for each Feynman diagram, but it holds for the sum over Feynman diagrams. For the sum over Feynman diagrams, for the gauge invariant sub-amplitudes, whenever one sees or wants to calculate a sum over epsilon mu alpha, epsilon star nu alpha, then one can replace that sum with minus g mu nu. Thank you. Let us now move on to consider Photon scattering. Now, this is an interesting process for many reasons. One of them is that this is the first process we have where we have external photons. It's also the first process where there are actually two Feynman diagrams contributing. So let's start by drawing all the Feynman diagrams. So Photon scattering is the scattering of electrons and photons. So an electron-photon scattering. So we have an incoming electron that scatters, incoming with momentum P, momentum K, momentum P prime, momentum K prime. So electron here, fermion flow in the arrow direction, momentum flow in the arrow direction is the E minus. Now, this is the initial state here. There's also a photon. Now that photon can connect here, and there's a photon in the final state. So this is one diagram. The other diagram is the one where the photons are connected in the other order. K, K prime, P, P prime. So, now that we've drawn all the Feynman diagrams, all two of them, we can calculate, we can use the Feynman rules to write down the expression for the amplitude. So we have Im is equal to, and we have to start, we have to always go against the fermion line. Now, first thing to notice here is that there's nothing like crossing fermion legs, identical fermions, anything like this that would say that there shouldn't be just a plus between the amplitudes here. So we start, it's the same fermion line that runs through. So we start with a U bar of P prime. Then we have the vertex here. Let's give the first vertex a index mu. Then there will be a minus IE gamma mu. Then there will be a fermion propagator, and from the first diagram here, that fermion propagator will be of momentum P slash plus K slash. Momentum flowing across here is P plus K plus M over P plus K squared minus M squared. Then there will be a vertex that we can give a Lorentz index nu. So there will be minus IE gamma nu. Then there will be the photon polarization vectors. I haven't put them in, but I'll do that later. I'll just follow the Fermi line through and say then there's a U of P. Now the photon polarization vector here will be a incoming photon, that's an epsilon star. So there's an epsilon star. The incoming one so the initial photon will have a epsilon nu of K, and the outgoing will be a epsilon star mu of K prime, using the rules for the incoming and the outgoing photons. Now, the epsilons are just polarization vectors in Lorentz space, so they can be put in anywhere in this chain. Doesn't matter where they go. But the spinors, the U, the 4x4 matrices in spinor space gamma, also denoted by the slash, and the M here, remember there's a 1 in spinor space, the gamma and the spinor U bar, column spinor, sorry, row spinor U bar, they have all to be in the right order, right? So we can't move them around, at least not without using any commutation rules. Good. So that's the first diagram. Let's take diagram 2. There will be the same fermion line, of course. So we start with a U bar of P prime, but if this is the mu photon, then now the first vertex that we get is the one that corresponds to the photon with the mu, right? Sorry, what am I saying? Mu is the K prime. Mu is the one that corresponds to the K prime, and nu is the one that corresponds with K, right, as we had it here. Mu corresponds with K prime, and nu corresponds with K. Completely confusing there. Mu is the one that goes with K prime, nu is the one that goes with K, as I've written down here. Good. So when we go for the second diagram here, the first vertex that we meet is the one that corresponds to nu. So that's minus IE gamma nu, and then we still have the same epsilon mu K, epsilon mu star, K prime. The external photons are the same, and then this time the momentum that flows across the fermion propagator here is P minus K prime. Good. So what we get here is I P slash minus K prime slash plus M over P minus K prime squared minus M squared. Alright, we go down with P, we then emit the photon K prime, so the momentum that flows across the propagator here is P minus K prime. Then we go further to the vertex with the mu, minus IE gamma mu, and then the incoming spinner, U of P. Good. Now, this, of course, can be simplified slightly. Let's just write it together. The spinner string is all the same, right? U bar, P prime, the propagator, U of P. So all of that the U's, we can take outside the bracket. But let's collect all the I's. So we've got a minus I, that's just, and an I, that's minus I. We've got two E's. Then we've got the polarization vectors, let's keep them here. So we've got an epsilon star mu of K prime. We've got an epsilon nu of K. And then let's start the spinner strings. So there we've got, let's write them down here, times then a U bar of P prime, and then we've got a gamma mu, we've got the P slash plus K slash plus M, we've got a gamma nu, and that's over P plus K squared minus M squared, plus, and then the contribution from the second diagram, that's a gamma nu, P slash minus K slash prime plus M, gamma mu over P minus K prime squared minus M squared U of P. Good. So there are a few simplifications we can make here, right? Because P squared is equal to M squared and K squared is equal to 0. So the denominators, P plus K squared is equal to P squared plus K squared plus 2P dot K, and this conveniently a minus M squared. So the propagator, P plus K minus M squared, that all evaluates as 2P dot K, and P minus K prime squared minus M squared evaluates as minus 2P dot K prime. Now, to simplify the numerators here with the Dirac matrices, we use a bit of the algebra for the Dirac matrices that actually defines them. So we note that P slash plus M gamma nu U of P is equal to 2 P nu, because that we can write P slash, right, remembering that P slash is gamma, is P mu, gamma mu. So when we have the gamma nu here, we can commute gamma mu, gamma nu to G mu nu. So we can write this as 2 p nu minus gamma nu p slash plus gamma nu m acting on u of p. Now the trick is that we want the p slash to come up close to the u, such that we can use the Dirichlet equation to simplify. So we get here, that's 2 p nu u of p minus gamma nu, and then here we have p slash minus m on u and p. But that's 0 by the Dirichlet equation, so that's 2 p nu u of p. Sorry, when I say the Dirichlet equation, I just mean the Dirac equation, and this is an on-shell spinner that satisfies the Dirac equation. Good. So if we use this trick in each of the propagators, then we can write the amplitude as I m is equal to minus I e squared epsilon star for the k prime, epsilon for the incoming photon, and then our spinor strings, now simplified u bar p prime bracket gamma mu k slash gamma nu plus 2 gamma mu p nu over 2 p dot k plus the contribution from the second diagram minus gamma nu k prime slash gamma mu plus 2 gamma nu p mu over minus 2 p dot k prime. And then finally the spinor u of p. So that's the amplitude. What we want to do is to calculate the cross section, so we need to square this amplitude, and in order to do that, or in the process of doing so, we will get the nice products of the polarization vectors that we dealt with previously, that will give us some g mu nu's that we need in order to contract the amplitudes nicely. So one could of course evaluate this amplitude using an explicit representation of all the spinors and the gammas, and then one would get a number for the amplitude for a given momentum configuration of the photons and the electrons. One would get a number for the amplitude. That complex number one could then square in order to calculate the cross section. That will be quite simple if one is comfortable with computers. Now instead, I will calculate here explicitly the square of this amplitude. In order to do so, we'll make use of some of the trace technology of spinners that we have developed. The most important thing to remember here is that when we have to form M, we have to form M star, but since M is a number, this complex conjugation and the Hermitian conjugation is the same thing. When one Hermitian conjugate a product, then that's equal to BA. So we have to remember that, because we've got here a long string of matrices. When we calculate the Hermitian conjugate of all of this, then all the matrices just come in the backwards order. So that's the one thing we have to remember. The second thing we have to remember is that for spinors, if we've got a U of K and a U dagger of k, and we sum over the spins of one up and down of the spinners, then we get here k slash plus m. So if we want to calculate the sum over polarization and spins for the Photon scattering, then when we calculate m squared, so that we want to calculate 1 over 4, the sum over spins of m squared, and that's equal to, of course, we can't forget the m when we take the mod here. So on the right hand side, we also forget the i's. We get an e squared over 4. That's the easy bit. Now let's look at the photon polarization tensors or vectors, sorry, that we get here. So the epsilon mu is contracted with the mu index of m. When we want to calculate m dagger, we of course can't use the same mu that we've used to calculate m, because then it would appear too many times in the equation. It can appear twice. The product lower and the upper. So for m, we use mu for outgoing photon, final state photon, and we use nu for incoming. This was with momentum k prime, and this was with momentum k. Now for m prime, or for m, sorry, not m prime, we want to calculate or write explicitly the complex conjugated m, then let's use something else. Let's say that we use rho for the outgoing photon with momentum k prime, and we use sigma for the incoming photon with momentum k. And that means that when we form m dagger or m star, we'll get a m dagger, which forms m squared. We'll get a epsilon mu dagger k prime epsilon nu k, but then from m star we would get a, let's start with this, so instead of nu we would get a sigma of k, and that will be star, and then of course we'll get an epsilon rho of k prime, and that's not star, it's starred here, but when we then calculate the complex conjugate, it loses its star. Good. So if we sum over polarizations here, then using the results that we just derived for epsilon star mu k prime epsilon rho k prime would give us a minus g mu rho, and the sum over polarization of epsilon star sigma k epsilon nu of k would give us a minus g nu sigma. So continuing our writing down of the matrix element up here, we would get a G mu rho G nu sigma. Now what's left then in the matrix sigma squared is a trace over all of this, right? We now dealt with the first line up here. Now let's deal with the bottom down line down here. So I'm writing here that's a trace over a complicated object. Now let's down here write that complicated object. Right? So what do we have? We have a trace, and that trace is something that starts with a U bar P prime, then we have a lot of matrices, and then we have a U of P. Now from M star, or M transpose conjugated, we would then start with a U bar of P, then we go backwards and have a gamma. Instead of a mu, it will be a gamma rho, and instead of a P mu, it will be a, oh, that was a gamma rho, and instead of the gamma nu, it will be a gamma sigma. And then you would get a gamma rho K slash gamma sigma, right? Because of the complex conjugation and the Hermitian operator. Now from the spinors, right? So you would go all backwards and you would end with a U of P prime. So let's say we start with what we had, which was a U prime of P prime, U bar of P prime, a lot of things, and then it would end with a U of P. Now comes the contribution from the complex conjugation and transpose. That would start with the U bar of P. Then we'd write a lot of gamma matrices, and then we would end with a U of P prime. We would have to sum this over the spins, and we remember that summed over spins, U of P, U bar, where did I write this up? With the Dirac equation, I'm not writing this, nope, okay, well, oh yeah, here, the sum U dagger gives us K prime plus M, right? So here, P prime or P slash plus M. Now what do we do with the spinors of the U prime? That's quite clever, because the trace is cyclic, so this long trace here is actually equal to, I'll move this all the way back here and get a U, P prime, U bar, P prime, and suddenly I can use the same trick and write, instead of this, when it's summed over spins, gives us P prime slash plus M, right? So all this complicated trace that I get, all the spinors for the electron, I will use the cyclic properties of the trace to write as P prime slash plus M or P slash plus M, and then all I'm left with are the complicated string of gamma matrices up here in the square bracket. Good. Let's write this down. Actually, what I then get is that the complicated trace is one that is P prime slash plus M square bracket gamma mu k slash gamma nu plus 2 gamma mu p nu over 2 p dot k plus gamma nu k slash gamma mu minus 2 gamma nu p nu 2 p dot k prime. That's what we had before. Now then comes the p slash plus m, and now we have to take the gamma matrices in the opposite order. And remember that before, whenever I wrote a mu, I now have to write a rho, and whenever I before wrote a nu, I have to write a sigma. So what I have here, let's write them in the same order in the addition as they come up here. You might think that it's a mu, and therefore I should write a rho, but you have to remember that in the complex conjugation and transpose, the gamma matrices come in the opposite direction now, in the opposite order now, so it's the gamma nu I should start with, and that gives us a gamma sigma. Then k slash gamma rho plus 2 gamma rho p sigma plus 2p dot k prime gamma rho k prime slash gamma sigma minus 2 gamma sigma p rho, like so. So I'll just define that as, sorry, that's all we need. I'll define this. I'll just say, when we write out this product, we can get denominators that are p dot k squared, we can get denominators that are p dot k prime, we can get denominators that are p dot k prime squared, right? But the p dot k prime can, even though the denominator is the same, that term can arise either from this term here multiplying that term there, or from this term here multiplying that term there. And even though that gives the same denominator, it gives two different numerators, and because they're matrices in spinor space, they don't commute. So let's not write them on the same fraction to begin with, but let's just say that we have something, let's call it 1, that has 2 p dot k squared, and that's this bit here with that bit there. And then there's a plus, something that is 2 p dot k, 2 p dot k prime. Let's say that that's this piece with that piece. The third spinor or complex gamma matrix traces will be 2 p dot k prime, 2 p dot k. Yes, the denominator is the same, but now it arises from this term with that term, and then plus the fourth contribution, which is this term here squared, 2 p dot k prime squared, where all these 1, to 4 are complex traces. Complex as in a little bit complicated traces. Now there's some symmetries here. When one goes through it, one sees that 4 is actually the same expression as 1 with k replaced with minus k prime. Also, one sees that 2 is the same as 3. Since, again, the traces are cyclic, so they can be completely, the order of the gamma matrices can be completely reversed. So the only thing that we actually need to calculate is 1 and 2, because if we know 1 and 2, we know 3 and 4 by simple substitutions. Now, let's show how one of these traces can be calculated. Let's just take the first one. So the first trace here is equal to the trace of p prime slash plus m, this gamma mu k slash gamma nu plus 2 gamma mu p nu p slash plus m gamma nu k slash gamma mu plus 2 gamma mu p nu. But we've used here the metric tensors g, rho, sigma, etc. to write the second set of gamma matrices with nu and mu. Now, there's 16 terms in here. Luckily, we don't have to calculate all of them, because half of them have an odd number of gamma matrices. Remember that the trace of gamma mu, gamma rho, gamma sigma, for example, is 0. Whenever there are odd number of gamma matrices, their trace is 0. So we only have to evaluate the half of the terms, the ones that are non-zero. And actually they can be evaluated quite simply by remembering again the commutation properties of the gamma matrices. So for example, if one has a trace of p slash prime gamma mu k slash gamma nu p slash gamma nu k slash gamma mu, as one would get, for example, if one took the p slash, the gamma mu, the k slash gamma nu, p slash gamma nu, k slash gamma mu, right? So the first term from each bracket. If one had to evaluate that trace, one would say that's equal to the trace. One would swap the gamma mu all the way here by using the cyclic properties of the trace. Then one has a gamma mu p prime slash gamma mu, and we remember that that's equal to minus 2 p slash prime. So here we will get a trace of minus 2 p slash prime, then it will be a k slash, and we will have the same thing here, gamma nu p slash gamma nu is minus 2 p slash k slash here. Then we use that what we want. Yeah, okay. So then we use here that in order we can replace the order of P and K by using again the cyclic property, or not the cyclic, this property of the gamma matrices, the commutator, anti-commutator. So that's equal to the trace of 4 P prime slash K slash to P dot K minus K P, which is equal to 8 the P dot K, and then the trace of P prime slash K slash where we used that when it doesn't hit the 2 P dot K, but the P prime dot K, P prime, K prime hits the K prime, then we remember that K prime is equal to K squared, which is 0 in this case. So half of this bracket vanishes. That's why we did the reordering here. That was in order to get the K prime, or the K slash, next to this K slash, so that we could set it to 0. Now, this then easily evaluates as 32 P dot K. The trace of P slash K slash is equal to just P prime dot K. Now, by repeated uses of such type of tricks, and Peskin and Schroeder has all the details, one can write the spin summed and averaged matrix element square. I'll just define that as a half times the sum over the photon polarization for each of the polarizations, and a half over the electron spin, but there's a half over each one, as 2 E4 P dot K over P dot K prime plus P dot K prime over P dot K plus 2m squared 1 over P dot K minus 1 over P dot K prime plus m to the 4 1 over P dot K minus 1 over P dot K prime squared. Now it's clear here that if one had dropped the mass term of the electrons, then one would get a much simpler expression here, and that's of course because that the traces would be much shorter, because the terms with the m would drop out. Now, in order to evaluate this matrix element, it is then convenient to choose a frame. Of course, m squared, m itself, is a Lorentz scalar. So if we evaluate it in one frame, it is the same value as we will get in any other frame, as long as the momenta are evaluated consistently in that one frame. Good. So a frame that is often used is the one where the electron, the incoming electron, is initially at rest. So we've got an incident photon, so that's the initial setup, and then what happens afterwards is that the electron moves with the momentum, the photon moves with the momentum. So if omega is the energy of the incoming photon and omega prime is the energy of the outgoing photon, then one can of course use energy momentum conservation to say that P plus K is equal to P prime plus K prime, and that means that P prime is equal to P plus K minus P prime. So if we take P prime squared, that's M squared, that will be equal to P plus K minus K prime squared, which is P squared, plus 2P K minus K prime minus 2K dot K prime, which we can evaluate as equal to P squared is equal to M squared, and with this choice of momentum as indicated in the figure in the lecture notes, we would have here plus 2m omega minus omega prime minus 2 omega prime 1 minus cos theta, because that P here only has the energy component. There's no momentum, no 3 momentum in there. And theta here is the angle between the incident and the outgoing photon. So that actually means we can subtract m and isolate for omega prime. That means that 1 over the energy of the outgoing photon minus 1 over the energy of the incoming photon is equal to 1 over m, 1 minus cos theta. Or we can find the energy of the outgoing photon as the energy of the incoming photon over 1 plus omega over m, 1 minus cos theta. Now, additionally, we can evaluate all the dot products in this m squared. We can evaluate in this frame by seeing that P dot K, since the electron initially is at rest, P dot K is equal to m omega, omega being the energy of the photon, m the mass of the electron, and P dot K prime is equal to m omega prime. Doing so, or using these, it's possible to condense the square of the matrix element into a very short form, saying m squared is equal to 2 e to the 4, the energy of the photon before the scattering divided by the energy after the scattering, plus the other way around, minus sine squared theta. Now, there's not too much to go down in order to calculate the cross section. I will leave the interested reader or the interested follower here to read Peskin and Schroeder for how to perform the phase space integral. I'll just state that the result is equal to d sigma d omega solid angle is equal to alpha squared over 2m squared omega prime over omega squared omega over omega prime plus omega prime over omega minus sine squared theta. Now, of course, one can check specific limits of this result. For example, the low energy limit, where the energy of the incident photon is much less than the electron mass, then by the result that we have up here, if omega is much less than m, then omega prime is equal to omega. So omega is equal to omega prime in this formula, one then finds that d sigma d omega is equal to alpha squared over 2m squared 1 plus cos squared theta. In all of these equations, of course, alpha is the fine structure constant, which is e squared over 4 pi, where E is the electron charge. Now this result here is the Thomson cross-section for scattering of just electromagnetic radiation of a free electron. There's another limit that's interesting. For example, one could consider a high energy photon hitting the electron. Now, in that case, one has that the energy of the scattered photon is m divided by 1 minus cos theta, and therefore the cross section d sigma d omega is approximated alpha squared over 2m omega 1 divided by 1 minus cos theta. Now this means that in this case the cross section is strongly peaked at small angles when cos theta is close to 1. That leads to a logarithmic enhancement in the cross section, in the local cross section, and therefore it's dominated, the total cross section is dominated by that small angle singularity. Technically, they will be regulated by the electron mass. But there is an enhancement at small theta.